Hello and welcome to this final video in the ECMI Modelling course Indoor Positioning. In this video we will take a look at Kalman Filtering. In this video we will introduce the idea of Kalman Filtering, we will introduce the Kalman filter algorithm, and in the last phase we will use the pathless model and the Kalman filter in MATLAB to produce our first positioning dataset. Let's first talk about Kalman filtering. It's also known as linear quadratic estimation. The Kalman filtering is an algorithm that uses a series of measurements observed over time containing statistical noise and inaccuracies and produces estimates of unknown variables. The method uses Bayesian inference and joint probability distribution to create more accurate results than what could be produced by single measurements alone. We will demonstrate this later in this video. The Kalman filter has numerous applications in technology such as guidance, navigation and control of vehicles, so it is quite natural that indoor positioning also makes use of Kalman filters. The algorithm itself works in a two-step process. First is the prediction step. The filter produces estimates for the current state variables containing some uncertainties. The estimates are based on a physical model. Then there's the update step, in which the outcome of the next measurement is observed. Then the estimates are updated using a weighted average with more weight given to the estimates with higher certainty. The algorithm is recursive and can run in real time by using only the present input measurements and the previously calculated state. For the purposes of indoor positioning, a model with constant velocity is useful and simple enough. We have to use some kind of a physical model, as mentioned previously, and the constant velocity model is good enough. We can model the state as a stochastic differential equation shown here, which can be discretized into a state model presented here. Here x is the state model estimate, phi is the state transfer matrix, and w is the state model error. The underscores k and k-1 means time step k and k-1 respectively. Continuing from the previous slide, the phi can be written as a matrix shown here. And we will also need the covariance matrix of the state model error and the measurement matrix. These can be found in the handout in the MATLAB demonstration later. Here is a picture of the Kalman filtering algorithm. So first we have some prior knowledge of our state. Then we have the error covariance matrix and x, which is the state model estimate at time step k-1 including k-1 time steps. We move to the prediction step and we update our prediction using a physical model that we have chosen. In our case it is the constant velocity model. We move to the update step, in which we compare predictions to measurements and we get the output estimate of state. Then we move on to the next time step and continue doing this process until we have used all of our measurements. And here is the Kalman filtering algorithm. So first you choose the first measurement, then you move to the prediction step. These formulas here are the same as in the handout and we will show them in MATLAB later. The important thing here is to see how the algorithm progresses. First we have the prediction step and then the update step, in which we calculate the Kalman gain using the predicted covariance, the measurement matrix and some noise. Then we calculate the updated state estimate using the predicted state estimate together with the Kalman gain and our measurements. And then we update the covariance using the Kalman gain and the measurement matrix. Finally, if k is equal to the amount of measurements, we stop. Otherwise we add 1 and go back to step 2 and continue using the algorithm. Here's an example picture of a random walk together with a Kalman estimate of the mean in blue. We will attain a similar graph for the x and y coordinates of our positioning. Next we will take a look at the Kalman filter exercise in MATLAB. The MATLAB exercise contains 3 parts. First, the pathless model will be applied to each access point in the dataset. Then we will calculate a rough estimate for our mobile phone user's position using the path loss model together with the test data file. After completing the model, we will use the Kalman filter for constant velocity to improve the positioning data created in the previous step. Let's now move to MATLAB and use the Kalman filter in practice. Okay, and welcome to the MATLAB side of things. Some of the things we will go through have been done in the previous 2 videos already and should be familiar to you by now. If they are not, rewatch those videos and you will get the hang of things. So we will now start by calculating the path loss model for each access point in the dataset. We load up the vel.data.mat file. Then we will create a matrix of nans that matches the size of the path loss parameters that we should acquire. For the LSQ nonlin, we can define some options. That has been done here. Especially we specify the number of maximum iterations and the maximum function evaluations. Then we move on to a for loop in which we calculate the path loss model for each access point. This has been done already in the previous videos for a single access point, and we're basically doing the same thing here. We have specified that we only use access points that have more than 20 measurements, so we have one if clause here, and we only accept the path loss parameters when the exit flag is positive. Exit flag is something that the LSQ nonlin function outputs. Finally, we save our path loss parameters to the matrix PL. Now that we have defined the path loss model for each access point, we can use this data to calculate the positioning of a user. We will use the data in test data to do this. First, we set up a matrix of nans, and then we convert the timestamps in our test data by multiplying first by 24 and then by 3600. Then we go into a for loop, but this time we are using the path loss model differently. We have only 2 unknown variables, the x and y coordinates of the receiver. This way we can calculate the estimate of position for the user. In our call for the function LSQ nonlin, our initial estimate is 0 for both of the coordinates. We have also specified some lower and upper bounds, and then the options that we defined earlier. Then we save our position estimate to the matrix pos_est. And finally, we use the Kalman filter to smooth out our position estimate. We enter the for loop, and we basically use the Kalman filter algorithm as was shown in the slides. We calculate the difference in time, and we state the state model tuning parameter and measurement noise, the state transfer matrix for constant velocity, the covariance noise, the measurement matrix, and the covariance or measurement noise. Usually this is non-constant, but in our example we will use a constant for this. Then we go into the prediction step. We calculate the prior mean, the prior covariance, and then we move on to the update step. We calculate the Kalman gain, the posterior mean, and the posterior covariance. Finally, we add the updated state into our dataset. By repeating the for loop, we attain a Kalman filtered position estimate. Finally, we can plot the x coordinates, the y coordinates, and the position with walls. Let's look at the plots. The first figure is for the x coordinate. We see that the red line is the true position, the black line is the static position estimate, and the Kalman filter applied to the static position estimate provides a better, smoother curve for the position. Next, similar thing for the y coordinate. And then finally, a plot of the position for an xy coordinate map. You can see the red line being the true path that has been traversed, the black line an estimate that has been given by the path loss model, and then the blue line being the Kalman filter estimate. Following the example provided here, you should be able to get started with your own project in indoor positioning. Good luck!